Catalysts and activation energy. Welcome to this presentation on one of the most important concepts in chemistry, catalysts and activation energy. Catalysts are the hidden engines of chemistry. They speed up reactions without being consumed, lowering the activation energy barrier and enabling transformations that would otherwise be impossibly slow. From the enzymes in our cells to the industrial catalysts that produce fertilizers and fuels, these remarkable substances make life and modern civilization possible. This presentation explores what catalysts are, how they work, their different types, and their profound impact on chemistry and industry. What are catalysts? A catalyst is a substance that increases the rate of a chemical reaction without being consumed in the process. The word comes from the Greek kataluein, meaning to loosen or to untie. The concept was first articulated by the chemist Elizabeth Fullamay in 1794. Catalysts work by providing an alternative reaction pathway with a lower activation energy. They can be recovered unchanged at the end of the reaction and used again and again. Over 90% of industrial chemical processes use catalysts at some stage. Yet crucially, a catalyst does not affect the thermodynamics of the reaction. The overall change in Gibbs free energy and the equilibrium constant remain exactly the same. The catalyst only changes how fast equilibrium is reached. Activation energy, the energy barrier. Activation energy is the minimum amount of energy that reactant molecules must possess for a reaction to occur. It represents the energy barrier between reactants and products. Even exothermic reactions require an initial energy input to break existing bonds and reach the transition state. The Arrhenius equation quantifies this relationship. The equation is K equals A times e to the power of negative EA over RT, where K is the rate constant, A is the frequency factor which accounts for collision frequency and molecular orientation, EA is the activation energy, R is the gas constant, and T is the temperature in Kelvin. A higher activation energy means a slower reaction at a given temperature. At 300 Kelvin, increasing the activation energy by just 10 kilojoules per mole slows the reaction rate by approximately 50-fold. How catalysts work. Alternative pathways. Catalysts provide an alternative reaction mechanism with a lower activation energy. The original high-energy pathway remains available, but most molecules take the easier catalyzed route. The catalyst stabilizes the transition state, decreasing the kinetic barrier. Imagine crossing a mountain range. The uncatalyzed path goes over the highest peak. A catalyst finds a lower mountain pass. The destination is the same, but the journey is far easier. A catalyst does not change the starting point or destination, the reactants and products, just the path between them. It does not change the reactant energies, product energies, or the overall enthalpy change. Only the kinetics are affected. Energy profile diagrams. Visualizing the effect. Energy profile diagrams show the potential energy of a reaction system as it progresses from reactants to products. The horizontal axis is the reaction coordinate, and the vertical axis is potential energy. For an uncatalyzed reaction, the activation energy barrier is tall. For a catalyzed reaction, a second, lower pathway appears. Crucially, both pathways end at the same product energy. The overall enthalpy change is identical. The catalyzed pathway may also involve intermediate steps, creating smaller energy hills instead of one large peak. On this diagram, you can see the uncatalyzed path shown as a dashed red curve, while the catalyzed path appears as a solid cyan curve. The two vertical arrows show how the activation energy is reduced by the catalyst. The Arrhenius equation and temperature. Svante Arrhenius developed his famous equation in 1889 to describe how temperature affects reaction rates. The equation reveals three critical insights. First, the exponential dependence on temperature. Even small changes in temperature can dramatically affect reaction rates. Second, the role of activation energy. Reactions with lower EA proceed much faster at the same temperature. Third, the frequency factor A, which accounts for collision frequency and orientation. The linear form of the equation, natural log of k versus 1 over t, gives a straight line whose slope is negative EA over r. This allows experimental determination of activation energy by measuring rate constants at different temperatures. A catalyst effectively shifts this plot upward by reducing EA. Typical uncatalyzed activation energies range from 80 to 200 kilojoules per mole, while catalyzed reactions have EA values of 40 to 100 kilojoules per mole. Homogeneous catalysis. Same phase. In homogeneous catalysis, the catalyst and reactants are in the same phase, typically all dissolved in a solvent. This allows every catalyst molecule to be accessible to reactants, often giving high activity and selectivity. Common homogeneous catalysts include acids, such as H+ for ester hydrolysis, and transition metal complexes. The 2021 Nobel Prize in Chemistry was awarded to Benjamin List and David Macmillan for the development of organocatalysis. Wilkinson's catalyst, EHCl, PPH3, is a famous homogeneous catalyst for alkene hydrogenation. The advantages of homogeneous catalysis include high selectivity and the ability to study the mechanism in detail. The main disadvantage is the difficulty of separating the catalyst from the products. Heterogeneous catalysis, surface chemistry. Heterogeneous catalysis involves a catalyst in a different phase from the reactants, usually a solid catalyst with gaseous or liquid reactants. The reaction occurs on the catalyst surface at specific active sites. The process follows 3 steps. First, adsorption. Reactants bind to the catalyst surface either through weak physisorption or stronger chemisorption. Second, the surface reaction occurs where adsorbed molecules react with each other. Third, desorption. Products detach from the surface, freeing the active sites for the next cycle. The high surface area of porous materials maximizes active site availability. This is the most common type of industrial catalysis, used in processes from petroleum refining to automotive catalytic converters. Iron in the Haber process and vanadium pentoxide in the contact process are classic examples. Enzymatic catalysis, nature's catalysts. Enzymes are protein-based biological catalysts that achieve extraordinary rate accelerations, up to 10 to the 17th fold. They operate under mild conditions, aqueous solution, near neutral pH, and ambient temperature. Each enzyme has a precisely shaped active site that binds only specific substrates through lock and key or induced fit recognition. Induced fit means that substrate binding reshapes the active site for optimal catalysis. Enzymes use diverse mechanisms, including acid-base catalysis, electrostatic stabilization, covalent intermediates, metal ion cofactors, and proximity effects. A single enzyme molecule can catalyze millions of reactions per second. Carbonic anhydrase, for example, can hydrate over 1 million carbon dioxide molecules every second. Industrial catalysis, shaping the modern world. Catalysis is the foundation of the chemical industry. The Haber-Bosch process for ammonia synthesis uses an iron catalyst to fix atmospheric nitrogen. This single process sustains approximately 40% of the global population through fertilizer production. Catalytic converters in automobiles use platinum, palladium, and rhodium to convert toxic emissions into harmless gases. The contact process uses vanadium pentoxide to oxidize sulfur dioxide into sulfur trioxide for sulfuric acid production. Petroleum refining relies on zeolite catalysts for cracking heavy hydrocarbons into gasoline. In total, catalytic processes generate products worth trillions of dollars annually, and approximately 35% of the world's GDP is influenced by catalysis. Active sites and catalytic cycles. The active site is the specific location on a catalyst where the reaction occurs. On heterogeneous catalysts, active sites are often at surface defects, steps, or crystal edges. On enzymes, the active site is a specific binding pocket. A catalytic cycle describes the series of elementary steps that the catalyst undergoes, binding reactants, transforming them, and releasing products, with the catalyst regenerated at the end. The turnover number measures how many reaction cycles a catalyst molecule can perform before deactivating. The turnover frequency is the turnover number per unit time and measures catalytic activity. The Sabatier principle states that the best catalyst binds reactants with intermediate strength, not too weakly, or the reactants cannot be activated, and not too strongly, or the products cannot desorb and the catalyst becomes poisoned. Selectivity, poisons, and promoters. Selectivity is a catalyst's ability to favor one product over possible alternatives. This is crucial in pharmaceutical synthesis, where unwanted byproducts are unacceptable. Catalyst poisons are substances that bind irreversibly to active sites, destroying catalytic activity. Sulfur and lead are notorious poisons. In catalytic converters, lead from leaded gasoline would permanently destroy the platinum catalyst, which is why lead-free gasoline became mandatory. Promoters are additives that enhance catalytic performance. For the Haber-Bosch process, the iron catalyst includes potassium oxide, calcium oxide, and aluminum oxide as promoters that increase activity and stability. Understanding these factors is essential for designing practical industrial catalysts that last. Adsorption, the first step in surface catalysis. Adsorption is the adhesion of atoms, ions, or molecules from a gas or liquid phase onto a solid surface. There are two main types. Physisorption involves weak van der Waals forces of 3 to 10 kilocalories per mole and is reversible. Chemisorption involves chemical bond formation of 20 to 100 kilocalories per mole and is usually irreversible. The Langmuir isotherm describes monolayer adsorption on a surface with identical independent sites. The BET isotherm extends this to multilayer adsorption. High surface area is critical. A single gram of a porous catalyst can have a surface area exceeding 1,000 square meters. Catalyst supports like alumina, silica, and zeolites provide this high surface area while keeping the active material dispersed. Advanced topics. Transition state theory. Transition state theory, developed independently by Henry Eyring and by Evans and Polanyi in 1935, provides a deeper understanding of catalysis. The Eyring equation relates the rate constant to the Gibbs energy of activation. The equation is K equals KBT over H times e to the power of negative delta G double dagger over RT. A catalyst lowers delta G double dagger by stabilizing the transition state. Some enzyme reactions also involve quantum tunneling, where particles pass through barriers instead of going over them. Autocatalysis, where a reaction product catalyzes its own formation, is particularly fascinating and may have been crucial for the origin of life. Self-replicating systems are essentially autocatalytic. Quiz question 1. Which of the following best describes the role of a catalyst in a chemical reaction? Option A. It increases the yield of products by shifting equilibrium. Option B. It increases the reaction rate by providing an alternative pathway with lower activation energy. Option C. It increases the temperature of the reaction mixture. Option D. It decreases the enthalpy change of the reaction. Take a moment to think about your answer. The correct answer is B. A catalyst speeds up a reaction by providing an alternative reaction pathway with a lower activation energy. It does not change the equilibrium constant or the yield. Thermodynamics is unaffected. It does not increase the temperature. It does not change the enthalpy change. The catalyst only affects kinetics, not thermodynamics. Quiz question 2. What does the slope of an Arrhenius plot, natural log of K versus 1 over T, represent? Option A, the activation energy. Option B, negative Ia over R. Option C, the pre-exponential factor. Option D, the rate constant. Take a moment to think. The correct answer is B. The Arrhenius equation in linear form shows that when natural log of k is plotted against 1 over t, the slope equals negative EA over r, and the intercept equals natural log of a. So the slope gives negative EA over r. The activation energy itself is calculated as negative slope times r. Quiz question 3. Which type of catalysis involves the catalyst and reactants being in different phases? Option A, homogeneous catalysis. Option B, heterogeneous catalysis. Option C, enzymatic catalysis. Option D, organocatalysis. Think carefully. The correct answer is B. Heterogeneous catalysis involves the catalyst and reactants in different phases, typically a solid catalyst with gaseous or liquid reactants. Homogeneous catalysis has the catalyst and reactants in the same phase. Enzymatic catalysis is a biological form of homogeneous catalysis. Organocatalysis uses small organic molecules and is typically homogeneous. Quiz question 4. In the Haber-Bosch process, what is the primary catalyst and what is its role? Option A, vanadium pentoxide, oxidizes SO2 to SO3. Option B, iron with promoters, breaks the strong nitrogen-nitrogen triple bond. Option C, platinum, catalyzes hydrogenation of vegetable oils. Option D, nickel, reforms methane into hydrogen. Think about it. The correct answer is B. The Haber-Bosch process uses an iron catalyst with potassium oxide, calcium oxide, and aluminum oxide promoters to break the extremely strong nitrogen-nitrogen triple bond in nitrogen gas, allowing it to react with hydrogen to form ammonia. Vanadium pentoxide is used in the contact process. Platinum is used in catalytic converters. Nickel is used in steam reforming. Quiz question 5. According to the Sabatier principle, what makes the best catalyst for a given reaction? Option A, the one with the highest surface area. Option B, the one that binds reactants the most strongly. Option C, the one with intermediate binding strength, not too weak, not too strong. Option D, the one that is most expensive and rare. Take a moment. The correct answer is C. The Sabatier principle states that optimal catalytic activity occurs at intermediate binding strengths. If binding is too weak, reactants cannot adsorb and be activated. If binding is too strong, products cannot desorb and the active site becomes blocked. This creates a volcano plot when catalytic activity is plotted against binding energy. Problem 1. Arrhenius plot analysis. An uncatalyzed reaction has an activation energy of 120 kilojoules per mole at 300 Kelvin. When a catalyst is added, the activation energy drops to 75 kilojoules per mole. Assume the pre-exponential factor A is 1.0 times 10 to the 13 per second for both. Part A. Calculate the rate constant for both reactions at 300 Kelvin. Part B. How many times faster is the catalyzed reaction? Part C. What temperature would the uncatalyzed reaction need to reach the same rate as the catalyzed reaction at 300 Kelvin? Use R equals 8.314 joules per mole Kelvin. Problem 2. Energy diagram interpretation. A reaction has the following energy profile: reactants at 50 kilojoules per mole, products at 20 kilojoules per mole, uncatalyzed transition state at 180 kilojoules per mole, catalyzed transition state at 110 kilojoules per mole. Part A. Calculate delta H for the reaction. Part B. Calculate IA for both pathways. Part C. Is the reaction endothermic or exothermic? Part D. By how much does the catalyst reduce the activation energy? Problem 3. Heterogeneous catalysis mechanism. The hydrogenation of ethene on a nickel catalyst follows the Langmuir-Hinshelwood mechanism. Part A. Write the three main steps of heterogeneous catalysis for this reaction. Part B. If the adsorption equilibrium constant K for H2 is 2.5 per atmosphere and the pressure is 1.0 atmosphere, calculate the surface coverage theta for H2. Part C. Explain why the Sabatier principle is important for choosing the right metal catalyst.